of low frequency IF enables performance to be high while keeping the cost below. That you are having a good, you can say better image rejection ratio in case of your low frequency IF. Accordingly, there are two conflicting requirements which cannot be easily satisfied using a single intermediate frequency, because you needed both parameters to be satisfied. You needed the better selectivity, you need the good image frequency ratio. This cannot be received or cannot be achieved by using one single intermediate frequency, because one single intermediate frequency can be high or it can be low. Both have their pros and cons. So both pros and cons has to be overcome or has to be given by using two intermediate frequencies. So the solution is to use a double conversion superheterodyne topology to provide a means of satisfying both the requirements. That is, you are having two intermediate frequency, one is high intermediate frequency and second is the lower intermediate frequency, so that you can achieve the advantages of both higher and lower intermediate frequencies. For good image rejection, relatively high IF is desired. However, for a high gain selective amplifiers that are stable, a low IF is necessary. So a high IF is also desirable and also a low IF is also desirable. So the solution for above constraint is to use two intermediate frequency. One is the higher intermediate frequency and second is the lower intermediate frequency. From first IF stage, the first IF is relatively high frequency for good image rejection, and the second IF is a relatively low frequency for good selectivity and easy amplification. So in case of your double conversion receiver or communication receivers, you are having the two intermediate frequencies. This is again the block diagram of your communication receiver. Here a detail of stages is given, that in the RF stage you are having the RF amplifier and a preselector block. In the first detector stage, you are having the first mixer that is attached to a local oscillator. Second input to your first mixer is from local oscillator, that is given further to band pass filter after providing the superheterodyne principle. After this band pass filter, you are again having a second mixer, that is this is the second detector stage. This again down converts your frequency into the second intermediate frequency, and the input to this second input is from again a oscillator, and again it is given to your band pass filter. After you are having the signal, it is given to the IF amplifiers and further to the audio detector. Now, why a communication receiver is named as double conversion receiver? As we have discussed that IF amplifier or IF is a trade-off between the high IF and the low IF. In your communication receivers, the solution is that you are having the two intermediate frequencies, one is high IF and second is the lower IF. So when you are down converting one RF signal into two intermediate frequency, so you are having two frequency conversions, you are having two frequency stages, you are having two mixes. So your RF signal is down converted into the two intermediate frequencies, one is the higher IF and second is the lower IF. So it is named double conversion receiver, as your conversion principle or frequency conversion is done twice in this your communication receiver, first as the first detector stage and second down converted at the second detector stage, that is at the second mixer stage. Now this is the basic block diagram of your communication receiver. Here you can see that what are the differences with respect to your superheterodyne receiver. In case of your superheterodyne receiver, you were having only one mixer, you are having only one frequency conversion there in the case of your superheterodyne receiver. But here, as we are having double conversion, you are having twice frequency conversions, one for higher IF and second for your lower IF. So you are having the two mixers, one is this first mixer that provides with your higher IF and second this second mixer that provides with your lower intermediate frequencies. And now after the signal is provided, it is given to the detector, then the audio amplifier, then to the power amplifier. That is similar that was in the case of your superheterodyne receiver. What next changes are there in the case of your superheterodyne receiver is, one is this beat frequency oscillator block that is added to this. Next is your Squelch circuit that is provided in case of your superheterodyne receiver, and the AGC that is here in case of your double conversion receiver. This AGC is your delayed AGC. Now, concept of intermediate frequencies at how the first IF is produced. We know that your intermediate frequencies, the difference component, that is local oscillator frequency minus the signal frequency. You are having the range for local oscillator frequency is 3.7 megahertz to 17.7 megahertz, and for signal frequency it is 2 to 16 megahertz. So the difference will be 1.7 megahertz. So your first IF is the higher intermediate frequency. This higher intermediate frequency is equivalent to 1.7 megahertz. Now after this 1.7 megahertz is achieved, after this first mixture, this 1.7 megahertz frequency is amplified by your IF amplifier stage. This IF amplifier stage again provide this particular frequency component to be processed in your second mixture. At this second mixture, the second input was from the crystal oscillator. So your second intermediate frequency is again f0 minus f1 as the difference component, that is oscillator frequency minus your signal frequency. Now here your oscillator was tuned at 1.7 megahertz. Here the oscillator can be a Hartley oscillator, and the frequency for this here you can here in the diagram you are considering a crystal oscillator for better stability, and it is tuned to the 1.5 megahertz. The difference between these two, 1.7 megahertz and 1.5 megahertz, it is 200 kilohertz. So this is your lower intermediate frequency. So you are having two intermediate frequency. One is higher intermediate frequency, that is for better image rejection, and second is lower intermediate frequency, that is for your better selectivity. So both these intermediate frequencies achieved your both the requirements, better image rejection and better selectivity. Other blocks that are there in the case of your communication receiver are delayed AGC. As I have discussed that in case of your communication receiver, the automatic gain control that you are using, it is the delayed AGC. Then is the beat frequency oscillator and the Squelch circuit. The disadvantage of your automatic gain control, that is attenuating weak signals, is overcome by use of a delayed automatic gain control. We have discussed this. Now this type of system develops no AGC feedback until you have established receive signal strength is attained, that is to a particular predetermined level you are providing no feedback. After that predetermined level is achieved, you are providing that feedback. For signals weaker than this value, you are not providing any AGC, and for sufficiently strong signal, delayed AGC circuit operates. The circuit uses two separate diodes that we have discussed. One is detector diode and one is the AGC diode, and AGC diode is connected to the primary of last IF amplifier. We have discussed this also. The positive bias is applied to cathode of AGC diode. This keep it from conducting until a prearranged signal level has been reached. After the predetermined level is achieved, the AGC will be provided. Before that level, your diode will be not working, that is the output of diode will be 0. There will be no reduction of gain for the weak signals. After the diode will be working for the stronger signals, you are providing the reduction in gain for your stronger signals. So the adjust delay control allows manual control of your AGC diodes. Manual control allows you to select the signal level at which AGC is applied. Here again the block diagram of your detector, practical detector stage is given. You are having two diodes, one is detector diode and one is the AGC diode. It is connected to this coupling capacitor. When a predetermined level is not achieved, your AGC is output is 0, your diode is not working for your weaker signals. But after a predetermined level is achieved, your diode is forward biased. At the output you are having the constant voltage, so reduction in gain is provided for your stronger signals. Now beat frequency oscillator, why this beat frequency oscillator is necessary? It is needed when you are going to operate on Morse code, that is you want to want that dots and dashes should be audible. We discussed the continuous wave signals. The continuous wave signals have the signals in the form of the dots and dashes, and if you want this dot and dashes should be audible, beat frequency oscillator is necessary when you want to receive continuous wave signals. The action of RF amplifier, mixer, local oscillator and IF amplifier is same for continuous wave and AM, but continuous wave signal reaches detector as signals frequency signal with no sideband components. So to produce an AF output, you must heterodyne, that is you must beat any continuous wave signal with an RF signal of proper frequency. That is the mixing process again. The separate signal is obtained from an oscillator it is known as your beat frequency oscillator. Now for example, considering that your intermediate frequency is 455 kilohertz and your beat frequency is tuned to maybe 456 or 454, so the difference will be of 1 kilohertz. 455 from 456 or 454, you are having the difference of 1 kilohertz, and this 1 kilohertz difference is heard in the output. Generally you will tune the beat frequency oscillator from front panel of the receiver. When you vary the BFO control, you are varying the output frequency, and the sensitivity of receiver is maximum when there is no signal received at your receiver point. This is the basic block diagram of your beat frequency oscillator with respect to your double conversion receiver. You are having RF amplifier, mixer, intermediate frequency stages. To the mixer you are having the local oscillator. Here the detector is connected to your beat frequency oscillator, considering that it can be for AM and CW both. Now this condition occurs, for example, when receiver is being, now when it is more sensitive and there is no input signal. So when this condition occurs, when the receiver is being tuned between station, at this time background noise is picked up. If you are tuning between various stations, the background noise is picked up by the antenna and you will hear noise that is greatly amplified, because amplifier cannot differentiate between the original signal or it is the noise signal. Now this noise is highly annoying and occurs because receiver gain is maximum without the signal. You are not having any input signal, but you are having a noise signal, and it is very annoying because this noise is being amplified by your amplifier circuit. So this can be overcome by using a switch circuit, also known as muting circuit. It is also known as your noise silencer because you are limiting the noise, a noise suppressor or noise limiter. All these are noise type circuits, and it just clips the peaks of noise spikes that are introduced in your circuit. So your Squelch circuit, that is muting circuit, will eliminate the noise. Now coming to the Squelch circuit, this is the basic block diagram of circuit diagram of your Squelch circuit. Here you are having in modulated signal, AF output, and the process is done by these two transistors. A switch circuit used to turn off the audio of a receiver amplifier when there is no RF signal. Without Squelch circuit, such absence of received signal will be heard on receiver as an annoying background noise. That is when you are not having any input signal, but the noise is present. Amplifier will amplify the noise and it will be appearing at the output. We don't need that. So that is overcome by your Squelch circuit. So for this, AGC, which is used to adjust the gain of receiver based on the strength of received signal, outputs a DC voltage that is proportional to received signal's amplitude. When carrier is absent, there is no signal present. This is due to delayed AGC. So this can be overcome by your muting circuit. This is the basic 2-point description that how it is overcome. In absence of received signal, output of AGC DC amplifier is very low. This very low DC voltage is fed to the Q1. This low base voltage causes Q1 to turn off. This transistor will turn off, resulting in base of Q2 being pulled up high through resistance R1, and this turns on your Q2. This is the case when it was received signal was absent. Now when there is the received signal, your Q1 gets a high base voltage from AGC amplifier and your Q1 will be turned on. Q2 is now pulled low by conducting Q1, causing Q2 to turn off. Now this Q2 is turned off. With Q2 off, the audio signal from Q3 collector is readily passed on to the audio power amplifier, as this connection is being terminated at this point. So what basically your Squelch circuit is doing, Squelch circuit is terminating the part between the first amplifier and your AGC, so that you are not hearing any noise at that point. Other features of your double conversion receiver is fine tuning, variable sensitivity and selectivity, noise limiting, better image frequency rejection, and better adjacent channel rejection. Now as we have discussed all three receivers, TRF, superheterodyne, and communication receiver, we can have a basic differentiation between these receivers. In case of your TRF, there was no frequency conversion. In superheterodyne, there was frequency conversion, but only single frequency conversion, that is only 1 IF. In communication receiver, you are having double frequency conversion, you are having 2 IF. In TRF, there was no IF. In superheterodyne, there was 1 IF. In communication receiver, there is 2 IF. Instability, variation in bandwidth, and poor selectivity was there in case of your TRF, and it was overcome in case of your superheterodyne, as you are providing the IF introduced. In communication receiver, also this has been overcome because you are providing the two intermediate frequencies, and the high and low IF provides the better selectivity and image frequency. TRF, in case of TRF, it is difficult to design tunable RF stages. In superheterodyne, main amplification takes place at IF. In communication receiver also, the amplification takes place at IF. TRF receivers are rarely used. Superheterodyne and communication receivers are mostly used. In TRF, there is concept of no AGC. In superheterodyne, AGC is introduced. In case of your communication receiver, AGC is you are using it as a delayed AGC. You are having two circuits introduced. One is beat frequency oscillator that is used with of your continuous wave, and the switch circuit is a muting circuit so that your noise can be eliminated. This was all about the chapter of your receivers. Thank you.